Day 2, we're looking at all logarithmic parent functions have a vertical asymptote at x equals 0. Their range, what was the domain on our exponential function? Anyone remember what the domain was for this? For the exponential function? You guys just did one, right? Negative infinity, it was all real numbers, right? So that was the domain. Now that x and y have switched, it's become our range. Our range for all, not just parent functions, but all logarithmic functions will be negative infinity to positive infinity, all real numbers. So that's true regardless of what transformations take place. Now our vertical asymptote and our domain can change depending on transformations that move that vertical asymptote or that reflect the graph across the y-axis, but the range will always be this. So we're looking at these. This has a base of 3. Is there anything else happening in this function? No. So what's the inverse of a logarithmic function with base 3? Exponential with base 3. So we're going to look at the table, and we should be familiar with this because you actually just generated it earlier today, for 3 to a power. So we got negative 3, negative 2, negative 1, 0, 1, 2, 3. I can do this by hand because 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, 3 to the third is 27. So then when I have negative exponent, it just does the reciprocal value. Well, that's great. We did that in lesson 3.1. So we were graphing exponential functions there. How does this help me graph the logarithmic function? Does anyone remember what I'm going to do? Switch x and y. So the same applies to the table. Log base 3 of x is going to have a table that looks similar, but it won't be exactly the same because the x and y will have switched places. So what was my x is now my y. And what was my y is now my x. So I'm going to try plotting what I can of this. It's not going to be perfect. Also, we had a horizontal asymptote of y equals 0 here. So now we have, like we said before, a vertical asymptote of x equals 0. So I'm going to sketch that first. My vertical asymptote of x equals 0. And then I'm going to plot these points. I'm going to plot them in green, I guess. 1/27th, which on the hour scale is basically almost on the y-axis. At that point, I go down to negative 3. 1/9, again, on our scale, unless I rescale this, is almost on the y-axis, negative 2. 1/3, I'm going to put it a little closer to 1/2, but it's not quite there. Negative 1. At 1, for the x, I don't go up or down, I just plot a point at 0. At 3, I plot a point of 1. Wait, what is this? I can't read it. It's a 9. That was supposed to be a 9. At 9, I plot a height of 2. And I can't fit 27 again unless I rescale the axis or rescale this graph. So there's our function, log base 3 of x, without any transformations done to it. That's the parent function. So I can get that without a calculator if I needed to. In this problem, we're asked to sketch the graph, describe the domain, range, intercepts, asymptotes, all that fun stuff. So the domain for this is restricted by one thing. What's that? The vertical asymptote. So it is 0 to infinity. Now that's what we set up here too, that it's always going to be 0 to infinity unless there's been a reflection or some other transformation, left or right. And then our range, well, it goes, this function is going down forever. It's a little hard to see. I didn't draw it very darkly. Let's going to continue going down, and it's going to continue going up as it goes to the right. So the range is negative infinity to positive infinity. That's always going to be true for all logarithmic functions. There is no y-intercept, but there is an x-intercept at 1, 0. The asymptotes, we have a a vertical asymptote at x equals 0. I'm going to scribe the end behavior off to the side over here. The end behavior is always related to our range. If there is a maximum height or minimum height or a horizontal asymptote, it's going to affect our end behavior. If we don't have any restrictions on our range, then we expect our end behavior to either move together in a positive direction or move together in a negative direction, or in this case, move in opposite directions. So as we go to the left, even though I can't go any further left than 0, as I incrementally get closer and closer to 0, this thing is shooting downward rapidly. So as I go to the left, from right toward left, it's going down. So the limit on the function, as I go toward the left, there isn't one. It just goes down infinitely. There is a limit on the domain, but not on the height. This is the height. There's no limit on the height. It shoots down infinitely. The limit on the height as I go to the right, there isn't one. It keeps going up infinitely. Now for exponential, that was different. We had a horizontal asymptote, so there was a limit. It couldn't go past that. But here we don't have anything interrupting the height of the graph, just the x value. Now, to describe the end behavior, normally we write an interval, some part of the interval of the domain. But as you start here, you've got this very steep, very small increments that you're moving toward the right, but you're going up. And you continue going up. Now it's less steep. So the entire domain, over the entire domain, we are increasing, or this function is increasing from left to right. Any questions on letter A? All right, let's take a little look at letter B. We're going to make a table again. This time our logarithmic function has a base of 1/2. There's no other transformations or anything like that, so I'm just going to look at its simple inverse, which is 1/2 to the power of x. Some of you are going, oh no, we got fractions, but it's actually not that bad, because what's the reciprocal of 1/2? 2. What type of exponent do I need to get the reciprocal of 1/2? Negative. So for -3, -2, -1, if I think, oh, well, the negative is the reciprocal, so now I have 2 to a power. This one's actually 2 to the first power, that's 2. 2 squared is 4. 2 cubed is 8. Because the base is 1/2 for the logarithmic function. So I'm using its inverse, and then I'll switch the x and y's. So now anything to the power of 0 is 1. Now it's the reciprocal. 1/2 to the first, it's the actual number. 1/2 to the first is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8, or the reciprocal of these. To get our function, our basic parent function of log base 1/2 of x, we're going to take this table and we're going to do what? Switch the x and y. Yep, flip the table. So, gosh, it's not 1, 2, 3, 4, 5, 6, 7. Yep. So my x's become my y's, and my y's become my x's. It'll be a little weird graphing this, because it's not going to be in the traditional order of left to right, which is how we're used to graphing. So now I go to 8. Oh wait, also where's my asymptote for this function? X equals 0, yes. Unless it's shifted left or right, this has a vertical asymptote at x equals 0. So I'm going to go to 8, and I'm going to go down to -3. Then I'm going to go to 4 and go down to -2. Go to 2 and go to -1. At 1 we have 0. And then I'm going to start doing them in green because it's hard to see with the red line. At 1/2 I have 1. At 1/4 I have 2. At 1/8 I have 3. So this graph looks a little bit different from the first one. For the first one, since it was increasing as we went to left to right, this is called logarithmic growth. Our base was a number bigger than 1. This one, our base is a fraction that's between 0 and 1. So this one is logarithmic decay. Because as I go from left to right, it's going down over the entire domain. Our domain is 0 to infinity again. Our range, once again, -infinity to +infinity. Our intercept, or it's actually the x-intercept, excuse me, once again is 1, 0. Unless we shift it up or down or left or right, then it would move its values a little bit. The y-intercept doesn't exist. The vertical asymptote still at x equals 0. Now the difference here is going to be in the description of the end behavior and the fact that across our entire domain this function is decreasing as we go from left to right. Who thinks they can accurately describe the end behavior for us? The limit on the height as I go to the left, and limit on the height of the function as I go to the right. I'll give you a hint, there are no limits. Yep, it's going, as I go to the left, even though I can't go any further left than 0, or even to 0, as you get closer and closer, it's shooting up, so you are correct. This one's +infinity, and as I go to the right, the graph is going down, so that's -infinity. Any questions on that? All right, so this is summarized in our table. This comes right out of the book for logarithmic growth versus logarithmic decay. Again, we're looking at the parent function. If you do any reflections, it's going to change it so that it doesn't look like this anymore and that it behaves differently. But the parent function itself, if the base is bigger than 1, it's growth. If the base is between 0 and 1, it's decay, just like exponential. But it's different than exponential in that it has a vertical asymptote. It has a domain that is restricted by the vertical asymptote. It has a all real number range. On the next side, we're only looking at these as base 10 right now until we review change of base formula for converting logarithms so that you can use them in the calculator. But we're just going to look at the graph. Compared to the graph of log base 10 of x, the common log of x, we're supposed to describe the transformation based on what we see and then sketch the graphs. We're just going to do a sketch. So we could use a table or we could do a sketch based on this table. So I'm going to do a table for this one, and I'm going to pick some values for x and y. So that's plenty. I'm not going to worry about more. Now, for log base 10, there's some that are really easy. If I want x to be 1, what does y have to be? So I'm saying, what's log of 1? What is it? Not quite. Remember, this is 10 to what power is 1? 10 to the 0 power. Now, if I do log of 10, what's log base 10 of 10? 1. I'm going to do that down here. I'm going to do my x value as 10 at 1. Because we don't have a graph more than this unless I want to change the scale, and I don't really want to do that right now, not with transformations. So I'm going to go to this table in my calculator, and I'm going to put in log of x. I'm just going to verify that 1 is 0, which it is, and 10 is 1. I'm going to pick some numbers in between those, like 3, 5, and 7, just to get some other points to plot. So I'll do 3, 5, and 7. It's going to give me 0.48, 0.70, 0.85. So that at least gets me some points to plot. So I'm going to plot the parent function on here, having its vertical asymptote at x equals 0. I have a point at 1, 0 and a point at 10, 1. At 3, I go to 0.48. Whoops, that's not 3. At 5, I go to 0.7. At 7, I go to 0.8. So it's going up very small increments until it gets to 10, 1. We also know that it comes down on this side and approaches the vertical asymptote. All right. Does anyone describe what's happening to this function based on that operation? It's inside with the x. It's going left 4. Transformation is happening going left 4. So basically I'm going to take all these points. I'm not even going to make a new table. I'm going to take these points and move them left 4 units. 1, 2, 3, 4. Make this one 1, 2, 3, 4. And I'm just going to do a sketch, so I really only need those 2. There's one other thing that I have to move left 4. What's that? Yes, the vertical asymptote. So I'm going to shift that left 4, so from 0 to -4. So this graph approaches that vertical asymptote, and then it comes up incrementally and hitting that point. So that's the same graph, it just shifted left 4 units. Take a moment to see if you can describe the transformations for letter B and for letter C. Just describe the transformations for letter B and letter C. Can anyone describe letter B for me? What transformations are taking place? The negative is a reflection across the x-axis, correct? Across the x-axis. And somebody thought this was right 5. What's the difference between this and this? This is in parentheses, so that's happening inside the logarithm. In this case, only the x is inside the logarithm, so the -5 is outside of that part, which means that this is down 5. So we're going to take our original parent function, and I'm just going to do a quick plot of the vertical asymptote 1, 0, and 10, 1, and just kind of do just a rough sketch, because that's all it asked for anyhow. Well, that's not a very good sketch, but whatever. We're going to reflect it across the x-axis. Well, what's going to happen to this point right here that's sitting on the x-axis? It's going to stay there. What happens to this point? It's going to be reflected to 10, -1. And then I'm supposed to shift it down 5 units. So I just move both of these down 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Does that change my vertical asymptote? Nope, still stays there. Didn't shift left or right, so that stays where it's at. This one is actually coming down as I go to the right, which means as I go toward my vertical asymptote, it's going to be coming up. So there's my sketch of the graph. Who can describe letter C for me? Isabella, can you give me one of the transformations? It does go to the left 2. That's what happens. To the x coordinate goes left 2. Who can describe what happens to the height of the graph? It is a vertical stretch of 3. Good. So now I'm going to, again, sketch the parent function just real briefly at the x equals 0. Put a point at 1, 0 and another point at 10, 1. There's my parent function. If I get stuck, I could always make a table with this. I can put in my calculator, get my table, that's not a problem. But now I'm going to shift these points and this vertical asymptote left 2 units. And then I have to do a vertical stretch of 3. Well, what's the height of this right now? 0. What's 0 times 3? 0. It's going to stay put. So this point stays locked in. This right now is a height of 1. If I'm multiplying that by 3, it should now be a height of 3. So this one comes up a little faster because of the vertical stretch. And there's my sketch of the function. Any questions on that? All right, so you guys are working on, that's why I had you pick up some graph paper on your way in. From page 178, we have problems 28 to 36, 38, 40, and 41. I have some recommended for review. If you want, I can give you those. Come see me, I'll let you know what they are. But these are the ones that match up to the skills that were covered in this lesson.